Good morning to all. Welcome to the next lecture on theorem proving techniques. First is mathematical induction, second is proof by contradiction. So that first of all we are starting with the principle of mathematical induction. As we had this method in earlier classes, that is in 11th and 12th, I'll be giving few examples and explaining the theory. First of all, the mathematical principle the principle of mathematical induction says that we have to make statement true for n is equal to k plus 1. But first of all, we have to check whether the given statement, whether the given theorem is true for n is equal to 1. Then we and this step is a basic step, and then we will assume that the given theorem is true for n is equal to k, that is where n is natural number. So we will assume that the given theorem is true for n is equal to k. Then we shall prove that theorem is also true for n is equal to k plus 1, that is pk plus 1 is true, that we will show. So that in that sense, if it is true for k plus 1, then we can see that theorem is proved for k plus 1 and any other natural number. Since we know that the difference between natural number, consecutive natural number is 1, so that theorem is true for every pair of consecutive natural number, hence it can be proved to any natural number, so that theorem can be proved. So first example we are taking, that is 1 plus 3 plus 5 up to 2n minus 1, that is sum of first n odd numbers. Fine, so that their sum is n square. So this is the theorem we have to prove by mathematical induction. So first of all, we check for p is equal to 1. So p is equal to 1. P is equal to 1, left hand side gives 1 and right hand side also give 1 ka square, that is 1. So that p1 is true. Now pk is true. We assume that pk is true, so that this statement is taken as true statement, and there it is. Now we have to prove for k plus 1, so that these terms are same. Last term k plus 1th term is added, and if we take, since we know that 1 3 5 up to 2k minus 1 has a sum of k square, then only in this k square we have to add the last term, that is 2k plus 1, and after solving this we get k plus 1 ka square. So that if it is k plus 1 ka square, then we shall say that the theorem is true for k plus 1 also. Hence theorem is true for 1 assumed to be true as at k and proved to be true at k plus 1. So it is true for all natural numbers n. Fine. Next देखिए, one more example, few more examples are given in this case also. So it is 1 square, 2 square, 3 square up to n square, that is n plus 1 to n plus 1 by this well known formula of sum of squares. So that first of all we say that p1 is true. We are saying this so that we check p1, left hand side and right hand side, both are equal. Now we say that for n is equal to k, this statement is true, so that 1 square plus 2 square up to k square is k plus 1 2k plus 1 by 6. Now we shall prove for k plus 1, so that one more term is added, that is k plus 1 ka square. Since we know that 1 square 2 square up to k square is given, and this sum can be equated to k plus 1 2k plus 1 by 6. Now we solve it, and we get a result for k plus 1 also, so that result is true for k plus 1 also. So it can be proved that it is true for all natural numbers n. Fine. Next देखिए, one more example it is given. Different type of example. Again, P1 is proved true, then Pk is assumed to be true, and then last term is added, that is k plus 1 term is added to the sum, and if we solve it we get this kind of sum. So it is true for k plus 1 also. So again we are saying that it is true for all natural numbers. Again, few more examples you can see. This is for every integer n, prove that 7 raised to the power n minus 3 raised to the power n is divisible by 4. So first of all we put n is equal to 1, so that p1 left hand side gives 4, that is divisible by 4, we know it. So that we assume that it is true for n is equal to k, that is 7 raised to the power k minus 3 raised to the power k is divisible by 4, so that we can put as 4d. Now for k plus 1 we solve it. Now this is step, please look at carefully. 7 raised to the power k plus 1 minus 3 raised to the power k plus 1 is this. We add and subtract one term, so that 7 is taken common with first two terms, and 3 raised to the power k is taken common in next two terms. So that 7 raised to the power k minus 3 raised to the power k is already known as 4d, and 7 minus 3 is 4, we know. So that both term having 4 as a factor, so that 4 can be taken out. So hence what we can say, that it is number is divisible by 4. So that theorem is assumed to be true at n is equal to k, and proved that it is giving say similar kind of result for n is equal to k plus 1. Hence we can say that theorem is true for all values of n. Again, one more example, similar kind of example is given, you can do this yourself. Look, 2 into 7 raised to the power n plus 3 into 5 raised to the power n minus 5 is divisible by 24. This question you can do, solution is given. Some more questions for practice are also given in this slide, you can do it yourself. Now the next method is proof by contradiction. Proof by contradiction, so that we can see next method, proof by contradiction. In this method, in this method, proof of contradiction, we assume that negation p, if we want p to be proved true, then we assume that negation p is true, that is conclusion p is not true. And if we start with negation p is true, then we reach at a false conclusion, then we say that negation of p is false implies p is true. So that this is the method. So very famous example, that is show that root 2 is irrational. How to prove this? First of all, we assume that root 2 is this is to be proved, but we assume that negation p is true, that is root 2 is rational, we assume this. So if it is rational, then root 2 can be written as a by b, that is p by q form, for some integer a and b having no common factor other than 1. We know that in a factor form, p by q form, p and q have nothing common other than 1, means their HCF is 1. So that if we write root 2 is a by b, we can write a is b root 2, and we square it, a square is 2b square, so that if a square is multiple of 2, then it must be an even integer, so that a square is even integer. So if a square is even, a is also even, it is a rule. So if a is even, it can be written as a is equal to twice k, that is multiple of 2. If we put a is equal to 2k in relation number 1, we get 4k square is 2b square, again b square is 2k square, so again b square is an even number, even integer, hence b is even. And if a and b both are even, they have common factor 2, but earlier we said that there is nothing common between them other than 1, so that we are reaching a false conclusion. So that what we are saying, that our assumption was wrong, that means negation p is false, that means p is true. P means root 2 is irrational is true. One more example is given. Prove that if n cube plus 5 is an odd integer, then n is an even integer using proof by contradiction. We shall prove by contradiction, so that we assume that it is n cube is, or if n cube plus 5 is odd, then what we have to prove, n is even, then but we assume n is odd. If n is odd, n square is product of two odd number, is again odd number. Similarly, n cube is product of two odd, that is n and n square, so again n cube is odd. So n cube plus 5 minus n cube is even, as sum of difference of two odd number is even, so that 5 is even. Look, n cube is proved as odd, n क्यूब प्लस 5 पहले से ही माना हुआ है कि वो ऑड है, तो दो ऑड का जब डिफरेंस निकालेंगे तो हमारे पास क्या आएगा, इवन नंबर आता है. जैसे अपन कहें 9 माइनस 5 दैट इज़ 4 इवन है, तो इसका डिफरेंस क्या आना चाहिए, इवन. लेकिन 5 आ रहा है इसका डिफरेंस, तो इस हिसाब से 5 क्या होना चाहिए, इवन होना चाहिए. लेकिन एज वी नो 5 तो इवन नंबर है नहीं, तो इसलिए हम कहेंगे हम किस पे पहुँचे, फॉल्स यानी कॉन्ट्राडिक्शन पे पहुँच गए. और कॉन्ट्राडिक्शन पे क्यों पहुँचे, क्योंकि हमारा अजम्पशन गलत था, यानी कि एन क्यूब प्लस 5 ऑड नहीं होना चाहिए, वो क्या होना चाहिए, इवन होना चाहिए. ये दो मेथड आपके सिलेबस में है. इस टॉपिक के सभी एग्जाम्पल आप अपनी बुक से करेंगे. कोई प्रॉब्लम होगी तो आप मुझे पिंग करेंगे. ठीक है, थैंक यू.